Hi guys, so we're going to talk about Concept 1 notes, and this should help you with your Concept 2 notes as well. And I'll make another video in the next coming days to help you with Concept 2 and Concept 3. But this is going to talk about stability and bonding. I'm going to go through a few of these a little quicker because we have talked about some of this information in past units. All right, in my first video, I reviewed some of the periodic table, what valence electrons are, the metals, non-metals, and a little bit of other things just to keep you reminded about our units prior to this. So combining elements, we're talking about compounds, which are two elements that are chemically combined. Remember, if they were physically combined, they would be called mixtures. We talked about that in a couple units behind, all right? So they're properties of compounds that are very different from properties of elements that make up the compound. So for example, sodium and chlorine are very different from sodium chloride. Remember, sodium chloride is what is table salt. That's what we put on our food. But sodium in itself and chlorine in itself are two separate elements. So we have chemical formulas, and this is used to tell what elements and how many of each of those elements are in a unit of a compound. So for example, H2O. Very common, we know what H2O is. It's our water. It contains 2 atoms of hydrogen and 1 atom of oxygen. Okay, it can be shown something like this. You have your 2 hydrogens, and it's all connected to 1 oxygen. And then our formula for ammonia, it contains 1 nitrogen and 3 hydrogens, just like that. All right, so why do elements form compounds? They want to become a compound to become stable. All elements want to be stable, and there's an octet rule that say atoms will gain, lose, or share electrons in order to have 8 electrons in their outer energy shell. So in order for it to be stable, it needs to have 8 electrons in their outer shell. So 8 total valence electrons. So stability is full or complete outer shell level of valence electrons. So 8 for every element besides hydrogen and helium. Let's talk about forming compounds. So here we have sodium and we have chlorine. This is the Bohr model for each of these elements, okay? Sodium has 1 valence electron. It's highlighted there in green. If it loses that 1 valence electron, the outermost energy level will be full and it will be stable. Meaning, if you take away that green valence electron right now and take away that energy level, then you will have the second shell having full 8 valence electrons. All right. Now, looking at chlorine, chlorine has 7 valence electrons highlighted just there. If it gains one of those electrons, the outermost energy level will be full and it will be stable. So you kind of want to think, is it going to be easier to take away those valence electrons, or will it be easier to just gain one of those electrons? We know sodium and we know chlorine are a common compound for table salt. So if we were just to combine that 1 valence electron of sodium into that chlorine, that means both of them will have a stable outer shell. All right. This is how the bond happens to form table salt, as we know is sodium chloride. Okay. Would elements ever not benefit from forming compounds? Yes, and that's if they're already stable. Okay. And if you look at your periodic table and you can see which one has 8 valence electrons, it's the far right group, which are known as the noble guests. Those are non-reactive because they already have 8 valence electrons in the outer. Everything's already full. So helium is the very top element of that group. It has 1 shell because it's in the first row. It has 1 shell, and the first shell can hold up to 2. And since helium has 2, that has a stable outermost shell, all right, with 2 valence electrons. Then neon, right below helium, it needs 8 valence electrons, which it does have, and same with argon. Okay? It might have 3 different energy levels, but the valence electrons are still the outer shell is completely full with 8 valence electrons. So we talk about bonds when atoms gain, lose, or share electrons in order to become stable, they form a chemical bond. Chemical bonds, the force that holds atoms together in a substance. All right, there are many types of bonds that can form. Not all bonds are created equal. Okay, we'll start by looking at ionic bonds. Ionic bonds are simply when atoms transfer electrons in order to be stable. Usually between, and this ionic bonds are usually formed between metals and nonmetals, which results in the formation of ionic bonds. Ions are atoms or molecules that have a charge due to having lost or gained electrons. All right. We start by talking about cations. We have cations, we have anions. But cations are positively charged ions. They are positively charged atoms that have a charge for losing or gaining their electron. All right. So these are atoms that have lost an electron. For an example, metals are metals. Magnesium. Magnesium shows that it has 2 valence electrons. All right. Because in order for that outermost shell to have 8, it's easier for magnesium to lose those electrons. Okay. And now you want to think that it's opposite. All right. So if you lose an electron, that means that it's positively charged. So magnesium would be positive or Mg positive 2 in that superscript. All right. So described here, magnesium has 2 valence electrons, so it will lose those 2 electrons in order to be stable, creating a cation, which is a positively charged ion of positive 2. All right? Ions, which is the opposite of cations. These are negatively charged ions, or atoms that have gained those electrons. So the opposite of cations, again, is where cations are metals, anions are, for example, oxygen. All right? Highlighted, we have our 6 valence electrons. In order to be stable, it needs to have 8 in there. So if 6 is closer to 8, so we're going to gain those 2 electrons from 6 to 8. Because we're gaining, you're going to take the opposite, and that's going to be negative 2. All right, so creating the anion with a negative 2 charge would make it oxygen negative 2. Let's look at this example for lithium. All right, so lithium is in the first group. So it has, this is the Bohr model for lithium. It has 1 valence electron. Okay. In order for it to be stable, we need to have 8 in this second shell. All right. So if you think yourself, would it be easier to just lose that 1 or gain 7? Which would be easier? For lithium, it'd be easier to just lose. Therefore, that first shell is completely full already. Okay? So, because you're going to lose that 1 electron, you're going to create a cation which is positive. So it would be Li positive 1. For nitrogen, it's got 5 valence electrons, but we need 8 because we only need 3 to gain. We're going to gain it, which would be opposite and have a negative charge, and then be nitrogen negative. For ions, very similar to valence electrons, elements in the same group have the same number of valence electrons. Because of this, the elements in the same group will form ions the same way. Okay, for example, lithium, sodium, and potassium, they're all in group 1, they all have 1 valence electron. So all of them will lose 1, which makes it a positive charge. So it'd be Li positive 1, Na positive 1, and K positive 1. All right. This is also known as the oxidation number, the charge of an ion within a compound. Okay, we talk about that superscript. Then, like, if you think of 2 to the power of 3, that 3 is written in the superscript. All right, so it's to the right of the symbol. So group 1 has a positive 1 charge. Group 2 has a positive 2 charge. You're going to skip, just like with valence electrons, you're going to skip 3 through 12 transitions metals. Group 13 has 3 positive charges. Group 14 has a positive or negative 4 charge because if you think about it, 8 valence electrons to create a stable shell for 2 and 3. If you have 4 valence electrons, it's just as easy to gain as it is to lose those valence electrons. Number 50, group 15 is a negative 3, group 16 negative 2, and group 17 negative 1 charge. How to build an electron dot diagram, all right, because we really only care about the valence electrons drawing this. It's not going to look like it's going to be similar to a Bohr's model, except we're only focusing on the valence electrons for all these. All right, it's called the electron dot or the Lewis. They're going to come out looking like this, or as shown with hydrogen, carbon, boron, and oxygen, and chlorine. This is the directions on how to write it. We follow the nucleus is represented by the atomic symbol, nitrogen is 10. Determine the number of valence electrons from group number and represent the valence electrons by drawing the amount of dots around the chemical symbol. So nitrogen we know is in the 15th group, meaning it's going to have 5 valence electrons. You're going to fill one side up before you pair electrons. So 4 sides, top, right, bottom, left. All right. So 1 valence electron, 2, 3, 4, and then we're going to start pairing them up, like create another circle, starting there at 5. So that is what our electron dot diagram. So if you did your practice, it should look like this. Hydrogen has 1, carbon has 4, fluorine has 7 valence electron, and phosphorus has 5. When using the dot diagram to show the bond formation, draw the electron dot structures, transfer electrons from the metal to non-metal, and add elements as needed. Continue transferring until all atoms are stable, and then write the chemical formulas using subscripts to show how many of each element were needed. Using sodium chloride. To draw the dot diagram, we know that sodium has 1 valence electron, and chlorine has 7 valence electrons. You want to think of this as a puzzle, all right? We know these two already formed together. So in order for sodium to have a stable, you want to lose this one because it's easier to lose than to gain another one. All right. So, and chlorine has a missing one, so it's almost like we can just put that electron right there. All right, now what about aluminum and chlorine here? All right, so we have 1 aluminum which has 3 valence electrons. Chlorine, we already know, has 7. All right, so we can put one of those puzzle pieces over there, or those valence electrons over there. However, we can't just leave aluminum with 2 valence electrons. We are going to have to create another chlorine that looks the same as the first one, and then we can put another one over there. And again, we can't just leave it with 1 more valence electron, so we need to take that last valence electron and add it to another chlorine. All right, and step number 5 is we need to create our chemical formula in order to say how many aluminums we have and how many chlorines we have. So looking at this example, we can see that we have 1 aluminum and we have 3 chlorines. And as you can see, that subscript shows how many chlorines we have. All right, and this is what we should have looked like. All right. Video. I'm talking about concept 2 in the next coming days, so make sure to look